I will be talking more about CFD modeling and its biokinetic integration. It has already been a little bit introduced in a couple of presentations already, so I will not go into detail, but I will try to give you a bit of an overview of what we have done in the context of LessWatt project, and then what this biokinetic modeling is capable of, and then a couple of case studies we have done in the project, and we'll try to find some conclusions. So if you compare it with the conventional flowsheet modeling, flowsheet models are very powerful models. It gives you like really dynamic modeling output. But what it does is that it assumes complete mixing, and in reality it might not be the case, which means it lacks that detail of the mixing. It normally models flow in only one direction unless it's not a compartmental model. The local variations which can originate from, for example, different design parameters like aeration or propellers or location of inlet are not really taken into account in the tanks in series model, and it can happen that they start deviating from the reality, and you have to somehow calibrate your tanks and series models to match your measurements. Whereas if you look at the computational fluid dynamic modeling, it takes into account the 3D structure and the design of your reactors, and it can model all the local variations up to like very small scale. This is something which is in your control, so you can really choose at what level of detail you want to model certain things. On the other hand, it's also computationally intensive, but it's getting more and more easy with the higher technology availability. So computers getting more and more stronger. So this resistance of doing CFD simulations is getting smaller and smaller. So this is like a general overview how these both approaches compare. The only thing which you would consider CFD cannot do now is the dynamic modeling, because it gets even more intensive. So what it does is that it provides you steady state simulations, which can be a snapshot of a whole bioreactor at a certain moment. And then what is really CFD biokinetic modeling? So CFD in general is like the flow modeling. So it models your flow, but it can incorporate different things. For example, it can consider your gas phases. So if you have aeration going on, it can consider that to calculate the mixing, for example. It can also take into account other properties of your liquids or of your gas, for example, rheology, so density, viscosity, etc. But a very important aspect is that it can also include kinetics. So kinetics it can be anything. So it can be chemical kinetics, biological kinetics. It can also include mass transfer, heat transfer, for example. In this case, what we have done is that we have integrated the CFD model with the biokinetics. And the biokinetics, we have used ASM1 model mostly. So what it does is provides you local concentrations of variables like dissolved oxygen, ammonium, and nitrates. So all the variables which are available in the ASM1 model can be actually calculated locally. And then what it does is it provides you the impact of the mixing and the local hydrodynamics on the performance. And it can be quantified. Okay, what if you reduce your aeration? What if you move your aeration somewhere else? What would be the impact on the eventual performance of the bioreactor? So this is a little overview of the biokinetic modeling, what we have done. The first case study we have is Kodapur resource recovery facility. It's 850,000 equivalent plant. What we have modeled is the aerobic part of the bioreactor. There are a couple of inlets you can see on this figure, and then there's an outlet on the other side, and then it's completely filled with all the diffusers at the bottom. Which means there's gas and there are liquids. So there are two phases being modeled in the CFD, and then on top of that we will add the biokinetics. We have tested different operational conditions with varying influent flow rate and the air flow rate to just test if what happens if you have reduced flow rate or higher flow rate coming into the bioreactor. And then at the end we also tested a lower flow rate, air flow rate scenario. This was a hypothetical scenario where we wanted to look at, okay, what will happen to the performance if you just reduce the air flow rate, which also Sabha showed that it had a very little impact on the performance but reduced aeration flow rate. But I will show you the results of that. So these are the velocity results. So velocity is the speed of the fluid which is going through the bioreactor. So what you see here are the 4 scenarios. So scenario 1, 2, 3, and 4 with different operational conditions. And then the colors of these vectors are actually the magnitude of the velocity, and the direction of these vectors are showing you the direction of the flow. So you can see it's very chaotic. It's just because it's completely aerated. So there's a lot of turbulence happening because of aeration. So you see different plumes being formed, and these graphs are taken from near the top. So it's near the surface of the water, but it shows you that there are different plumes and different formations of the water flow patterns are being formed. What you can see here in the scenario 4, where we reduce air flow rate, you see a bit less flow or the velocities of the water. And the rest, more or less, the velocities are similar, but they are different a little bit here and there just because of the different operational conditions. But overall, they were very similar in general. And then if you look at from the vertical angle, you will also see that they're all at the same location, but you see different flow patterns being formed. These are the plumes which are formed because of the air. So these vertical vectors show the formation of the plume, and in some cases they are different. In some cases they are much stronger, and it just at a certain location, if you move it further, it would change. So they are like very turbulent conditions in the bioreactor, which is leading to different mixing patterns. Okay, and then if you look at the biokinetic results, so this is the result of the integration of biokinetics with the CFD. And as I said, that you can actually look at the different ESM1 variables like dissolved oxygen. So what you see here is that if you go from lower flow rate towards a higher flow rate, the overall oxygen is reducing. Dissolved oxygen is reducing just because you have higher load coming into the system. And if you see, for example, here you have lower aeration, so you also expect lower oxygen, dissolved oxygen in the bioreactor. But overall, it's a very good plug flow, so it goes from left to right, or from this side to the other side, and you see a very plug flow behavior, which also Saba showed that we can actually model it very well with the Tanks and series model already. So this was already a very good learning from this. In similar fashion, you can see different variables like this is solvent substrate, which enters at a higher concentration, leaves at a very low concentration, and the impact of different flow conditions on the substrate is visible across these 4 scenarios. Similar, if you look at ammonium, you are almost removing the ammonium in the first scenario. Here, the local HRT is lower because you have double the flow rate, so you do not completely convert your ammonium, so you still get a lot. And in this case, it's an extreme situation where you see that higher ammonium concentrations are present at the outlet. But in this case, if you compare from 4,000 with the 4,000, but at the lower aeration, you see that even though you have reduced the aeration, you still have significant ammonium removal. It just takes a bit longer into the reactor, but eventually at the outlet, you would have more or less the same concentrations. So this shows that actually at a lower aeration, you can also not only reduce the aeration, but also keep the same performance of the bioreactor. Similar nitrates, eventually because you are reducing the aeration, the nitrate formation is lower, and the consumption becomes higher compared to the production. So eventually you get lower nitrates at the effluent. So it also improves the performance, not only reduces aeration. Here we have just quickly compared the 2 scenarios where high and low aeration. You can see, of course, with the lower aeration, you would have lower dissolved oxygen at the effluent. But if you look at the concentrations of soluble substrate, ammonia, and nitrates, they are not significantly changing, which tells you that you can actually get to the same performance by lower aeration. So this is already a very positive, what Saba already showed. So this was Codeper resource recovery plan. Then we have San Colombano. In San Colombano, it was a bit more complex. So you had an anoxic zone in the beginning, and then you had an aerobic zone in the rest of the reactor. The anoxic zone was with all these baffles. So water was coming in from here. It goes through different baffles like this, and then enters into this into the big aerobic zone. In the aerobic zone, you have a lot of diffusers on the bottom, and then you have this internal recycle, which takes water from the aerobic zone and puts it back into different parts of the anoxic zone. And then you have also a RAS inlet and a wastewater inlet in this corner. And then you have also these little mixers in the different corners of the anoxic zone. So this was a bit more complex than the quadrupole treatment plot. Here we as well model different flow conditions, three flow conditions, but at the end they were very similar with respect to the load, and that's what we would see in actually the results as well. Again, this is the velocity vector which I introduced earlier. This gives you the magnitude of the flow and also the direction of the flow. And what we learned from here that they are changing a little bit over the scenarios, but there is not a major shift of flow patterns happening. And this is mainly because you have the propellers which are actually functioning across the scenarios in a similar fashion. So they they are driving the whole flow in a very similar fashion. And then if you look at the biokinetic models, we have dissolved oxygen. Dissolved oxygen in this case is very similar across the scenarios. The only difference was that in the scenario 1, we had a lower aeration. In the rest, we had more or less the same aeration. And one very interesting thing what we found was there was actually oxygen flow coming back into the anoxic zone, what you see here. Actually, this last compartment is supposedly anoxic, so it should not have any oxygen, but there is an oxygen flow coming back into this zone, which eventually actually is actually making your anoxic zone smaller compared to the reality, or compared to what you would have intended it for. And then eventually, if you look at the nitrates, nitrates are then eventually being produced in the aerobic zone, but they're also being produced here in the last compartment of the anoxic zone. And then there's also recycled, so they are being recycled. So you see higher nitrates even in the earlier compartments as well. Ammonia conversion is very good in all the scenarios, except for this little bit. You still find some ammonia in the last compartment, but actually ammonia conversion is very good across the whole reactor, and then it enters into the aerobic section and it completely is removed. And then if you look at the effluent concentrations, you would see that they are more or less very similar. Only for scenario 1, where you have lower aeration, you had a little bit higher nitrates. Sorry, I think it was higher aeration in the scenario 1, which led to higher removal of ammonia and higher nitrate production and higher oxygen concentrations in the effluent. So all in all, what we can conclude out of these simulations is that CFD biokinetic modeling gives you a very good idea on the impact of your hydrodynamics, of your design on the performance of the bioreactors in a very good resolution, and eventually you can also calculate N2O emissions based on your oxygen concentrations, for example, and it can serve as an input for your N2O risk model as well. And if you don't have a very good mixing, you can also convert your flow sheet model, standard flow sheet model, into a compartmental model to make it even better for dynamic modeling. And what we've also observed is that even at the lower aeration rate, you actually have very good process performance, which normally is always a bit of a question. Okay, if you would reduce your aeration, in which direction your performance would go? So these models can actually help you in assessing that if you would reduce your aeration or you change your aeration rates, how the performance would happen. And eventually this tool can be used to improve the design. So moving the baffles, removing or adding the baffles, or changing your impeller design or location, or the RPM, or the aeration diffuser locations. It can help you actually improve your design and operation of the bioreactors. So yeah, thank you. That was it.